Hey, my name is Dr. Dan Look, and I'm a mathematician and a mathematics professor at St. Lawrence University. And today I want to chat a little bit about something I love, which is fractals. And they really are the geometry of nature, and I want to kind of talk about why. So, we're going to start in a weird place, and that's border lengths. So, Portugal and Spain share a border. And in 1951, the Portuguese reported that border length as 987 kilometers, while the Spanish reported it as 1214 kilometers. Border lengths are important in international relations, right? So it's important to know which one of these is correct. There's a pretty big difference there. Well, we're going to start by doing a related problem called how long is the coast of Britain? Because it's going to turn out that the answer to this question is similar to the reason that we get these different lengths for the border between Portugal and Spain. It turns out that coasts are tricky to measure. And this is important as the border between Portugal and Spain is a river, right? And so when you have a river, you have the coast or river bank along each edge. And as I mentioned, those are tricky to measure, and I want to explain what I mean by that. So we're going to explore this with the coast of Britain. And this turned out to be actually, there's a pretty famous paper called How Long is the Coast of Britain that explores exactly this. So here's an example of an image of the coast of Britain. We're going to measure the coast using line segments of a fixed length. So you're going to start at a fixed point. We'll always start way down here in the lower left corner. And see, there's my first red line segment. I start at that lower left corner and I move across to another point on the coast where that red line segment hits. And I try to move to the closest point on the border where that line can be made to end. And that would be right here. I could also obviously flip it up and go here, but I'm going to choose to go around this counterclockwise. And now I'm starting here, and I need to go another length, and so I'm going to kind of lay down my ruler and move it and see where does it next intersect the coast, and it's right here. And then I'll keep doing this, working my way around. Now, at some points, you'll have multiple spots you could choose for where it ends. If you have that, always choose the one that's closest to where you are if you were walking along the coast. And when you reach the last line segment all the way around, most likely it's not going to line up exactly right with the length that we have. So you probably need to approximate the length of that final segment. And when you're done doing this kind of thing, we can add up the number of line segments and get an estimate of the length. So I've got a handout for you, and there are 3 ruler sizes provided at the bottom. It's the Coast of Britain handout. It's got a picture of the Coast of Britain, and then there's little rulers at the bottom marked 1/4, 1/2, and 1. What I want you to do is use 1 or 2 or all 3 of them, depending on how you want to go through this. Maybe break into groups, and one does a fourth, and the other one does a half and 1, or everybody does all 3 of them. As a warning, 1/4 being the shortest will take you the most number of steps to get around. You can probably do 1/2 and 1 in the same amount of time it takes you to do 1/4, but in about 10 minutes you can probably get all 3 of these done. And I want you to determine the length in terms of the number of line segments. As an FYI, another way you could do this is obviously just using an actual ruler and figuring out what my little 1/4, 1/2, and 1 correlate to. Or you could use a protractor, right, and set up the protractor, right, if it's protractor, set it up so that it matches the lengths, lock it in, and then just kind of walk around. Right? Units matter. So since I've just given you 1/4, 1/2, and 1 with no unit on there, I think 1 is roughly 3 inches maybe, I'm not sure. But I'm going to suggest using the length marked 1 as the unit. So whatever unit is, it's 1 unit. That means that if you're using the 1/2 measure, you're going to get twice as many of these line segments as well, I should be careful with that. That's not quite true, as we'll see in a second. What I will say, though, is if you're using the 1/2 measure, you will need to divide the number of line segments by 2. And if you're using the 1/4 measure, you'll divide the number by 4. You can also think of it as just multiply the number of line segments you got by the ruler length, 1, 1/2, or 1/4. So pause here and do activity 1, and we'll come back together and see what we get for those lengths. Okay, so when I did it, here's my first using line length 1. You can notice it's a terrible approximation of the coast. I'd be fired immediately if I was my job to tell you how long the coast is, and this is what I gave you. But using this, I have 1, 2, 3, 4, 5 line segments. And then a little tiny line segment down here. that accounts for that 0.75. I estimated that as 1/4 of a 1 unit, right? So we get 5.75 here. For the second one, I get 1, 2, I think there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then a little tiny bit over here. I think I called that roughly a half, so it's 15.5 of the line segments, but I got to divide that by 2, which gives me 7.75 as my length. This one's doing a better job. It's starting to hug the coast a little bit better. My last one, doing it with 1/4, is not bad, but again, you can still see we're missing large gaps, right? The coast is longer. And in this case, I got 8.875 when I went through that. So we can see the coast gets longer as the ruler lengths get shorter. That's not really that surprising because you can see I'm doing a terrible job of approximating. What is surprising is what happens as you continue to shrink that. So here's an actual approximation. Length is 3,193.54 kilometers with this ruler. With the next one, 3,198.35, and then 3,834.2, and then we really refine it and we get 8,321.84. This is getting quite a bit longer, right? From 3,000 to 8,000. It more than doubled between these two. It turns out there's something called the coastline paradox behind this. As the line segments get smaller, the length gets longer. That's understandable, but here's the weird part. Theoretically, the length increases without bound as you make these things get smaller and smaller and smaller. That means in some way that there's no fixed length for a coastline. You could even say they're infinite in some cases. This is known as the coastline paradox, and we want to explore this a little bit. And we're going to explore this with something called fractals. So the issue is the crinkliness of the coastline, right? How wrinkly and crinkly it is. Geometry typically uses lines and sometimes circles and things like that, like for circumference to measure distance. But lines fail with something like a coastline. For most geometric objects, if you zoom in enough, things look relatively smooth and a line does a pretty good job of approximating it, but not for coasts, right? When you zoom in on a coast, the image you get looks like a coast, right? It's really hard to tell scale just from the image, right? Here's, again, Britain in that little white box. I'm going to zoom in on that. Here we go. Looking at this, I cannot tell anything about how big, what the dimensions are here. Zoom in on that new white box. Same thing. I see what looks like a coast. Zoom in on that white box there, then zoom in again. Notice on this one, I start to see roads, so I can start to maybe guess, my scale. But up until that point, it just all looked like coast. There's no way to know how long these things are, which means every time I kind of zoom in, I've got to go in more and more of these little crinkles and crags and around to trace this out. And guess what? If I zoom in on this little spot here, I'm going to see more little crinkles and crags going in and out. That's going to cause my length to increase as the ruler gets shorter and shorter. This is known as self-similarity, the idea that we take the whole image and zoom in on it and it kind of still looks the same. That's self-similarity. Benoit Mandelbrot coined the term fractal to refer to such objects. So here's an example, and we're going to explore this one a bit. We're going to move away from coastlines and start talking now about pure geometry. So we're going to create something called the Koch curve. So we start with a straight line, and then we erase the middle 1/3 of that line. Now we've got two line segments, each 1/3 the length of the original, with a space in between. And I'm going to fill this space with 2 copies of these lines, making a triangle. So now each of these 4 lines is they're all the same length. They're 1/3 the length of the original. And what happens with the Koch curve is you keep doing this. Next we delete this little line segment, put a little triangle here, and we get, here's the first, the second. Here's what it looks like on the 3rd iteration is what we call these. On the 4th iteration, we get this. On the 5th iteration, we get this. And the resulting thing, this is only 5 iterations, but if you did this forever, the resulting thing is the number of iterations goes to infinity, which involves an idea of limits, which we don't need to get into here. But the resulting image is what's called the Koch curve. It's pretty crinkly. So how long is this curve? Well, in the following activity, we're going to find the length at each of these steps, at each of these iterations. So let's pause and do activity 2, and then we'll come back and chat about that. Okay, so here's the handout that you had for activity 2. This is the first question. If the original line is length 1, how long are the following curves? So at each step, a hint, remember that the new line segments are 1/3 the length of the previous, and you should also remember that there's 4 times as many line segments as there were for the previous, right? You can kind of see that here. This one becomes these 4. This one becomes these 4, and we can see what's going on. So in the beginning, you can just literally count them. There's 4 of them, and they're each 1/3 the original. That's 4/3. The middle one, you can still count them, but getting a little annoying to count them. And we see that there are actually 16 of these line segments, and they're each of length 9. That's 16/9. Oh my goodness. The next one, if you chose to count these, that's okay, but it's a lot of counting. It's 64 of those things, and they're each 1/3 the length of the last one, which is 1/3 of 1/9 or 1/27. So 64/27. Okay, but you may have seen there's a way we can get this length without counting all those number of little, right? We don't need to count all the little lines. We don't need to count to 64 to get that. So here, question 2 was to find a general formula at the nth step. Well, notice that for n equals 1, we had a length of 4/3. When it was 2, it was 16/9 or 4/3 squared. Again, that makes sense. Each line segment is becoming 4 line segments. So we multiply the number of line segments by 4 each time we do an iteration, and the length gets divided by 3 each time we do an iteration, and that's our 4/3. And then 64 over 27 is 4/3 cubed. And in general, it's 4/3 to the n. This is exponential. And it's exponential with a base, 4/3, that's bigger than 1. This gets bigger and bigger and bigger as n increases. So the length of stage n is 4/3 to the n, bigger and bigger and bigger. As an example, by the time we hit stage 30, the length is 5,599.67. If our original line was 1 inch, right, 1 inch between my fingers, then at stage 30, it's almost 467 feet. That's really long. But it's still in between my fingers, right? It's not like we've stretched the thing. It's just gotten crinkly. So that 467 feet, you're between my fingers. It's 1 inch apart. I don't know what that would be, but say it's here. It's the Koch curve. You start walking along the curve. You're a little tiny bug. You're trying to get your steps in, right? You walk along that curve. You've walked 467 feet before you get that full inch between my fingers. And the length approaches infinity as we continue. Again, this is a concept of a limit. If you know what limits are, awesome. You can kind of look at this and make that mesh with that understanding. If not, just think of it as n gets bigger and bigger and bigger, so does the length, and without bound. This means that if you had the actual Koch curve, where you've done this an infinite number of times, it's still between my fingers, but it's now infinitely long. So a little tiny bug trying to walk across that curve would never make it to the end. By self-similarity in this case, it's exactly self-similar, meaning we can take little pieces like this, and if you blew that up, it would sit on top of the whole thing. And here's another piece. It's kind of at an angle, right, and a little bit smaller, but again, you rotate it and blow it up, it looks just like the entire curve. That's the idea of self-similarity, and this crinkliness comes into play with self-similarity. I have another animation for you that's kind of cool. If we take 3 of these Koch curves and put them together, we get something called the Koch snowflake. And you can see it makes a pretty nice little snowflake. Now, here's where things get really wonky. Remember, each of these Koch curves, and there are 3 of them here, they each have infinite length. That means the Koch snowflake has an infinite perimeter. You could never trace out the edge of it. But it has finite area, right? I mean, it fits on my computer screen. So the Koch curve has finite area and infinite perimeter. That is not something that happens in traditional geometry, but it is very common in fractal geometry, where we're kind of breaking the rules a little bit and, again, considering these self-similar crinkly objects. Okay. This brings us to something called fractal dimension. We're going to explore a little bit to see some really, really neat and weird stuff. So first, what is dimension, right? You've probably heard that like a line is one-dimensional and a square is two-dimensional, but what does that mean, right? Well, one definition is in terms of freedom of movement for directions, right? In a line, you can pretty much go one direction, forward and backwards. In a square, if you think of north-south as one direction, positive going up and negative going down, and east-west as another, then combinations of those two cardinal directions give you the entire two-dimensional square, and 3 dimensions you can do the same thing. But there's another definition that's a little more interesting, and is specifically for self-similar items. So let's see what happens when we do this with a square. All right, so I've got my square here. The L equals 1, that's the side length is 1, right? Here I've divided the side length by 2, but now I have 4 copies of my original, 4 little tiny copies of the square, right? They're self-similar. You blow that square up, you get the whole thing. When I divide the side length by 3, I get 9 copies. If I do this for a cube, I have 1 copy when I leave the length alone. When I divide it in 2, all of a sudden I have 8 of these little cubes. When I divide it by 3, I've got 27 of these little cubes. Okay, there's something going on here. So to make notation easier, I'm going to call n the number of self-similar pieces, and m will be the magnification factor, which is 1 over L. So back here, my n is 9, and my magnification factor is 3 for the L equals 1/3. And one thing that means is that you take one of these little 9 pieces, and if you magnify its side length by 3, you get something that's the size of the original. Okay, so for the line, m equals 2 gave n equals 2, and m equals 3 gave n equals 3. For the square, 2 gave 4, and 3 gave 8. For the cube, 2 gave 8, and 3 gave 27. I don't know if you see the pattern yet. Well, in general, it looks like n, the number of pieces, equals m raised to the d, where d is the dimension. We want to solve for the dimension, and we can do that using logs, those things that we often hate, right? But log has a special power when it comes to things in exponents, right? They kind of undo them. So n equals m to the d implies that the natural log, you can use any log you want, but we'll use the natural log, that the natural log of n equals the natural log of m to the d, but remember that special power of logs, exponents jump out front. So we get d times the natural log of m. Dividing by log of m means that d is log n over log m, which is called the fractal dimension. So here's a fractal. This is the Sierpinski triangle. We haven't talked about this one yet, but notice it is definitely self-similar. So let's try to figure out our n and our m for this to figure out the dimension. So here's a self-similar piece, and notice there are 3 pieces that are the same size as that. So n would be 3. What is m for this particular bunch? Well, remember, we're looking at side lengths. So the side length, if this is 1, this is now 1/2. So my m is 2, and my n is 3. That means that the dimension is log, sorry about the missing parenthesis there, is log 3 over log 2, or, whoa, 1.585. This stupid thing exists between dimension 1 and dimension 2. And it turns out, right, notice these 3 self-similar pieces, that's just one example. I could have also chosen this little dude up here, right? That could be my self-similar piece. And then how many do I get? I get all of these, right? What's that? 1, 2, 3, 4, 5, 6, 7, 8. There's 9 of them. Now what's my side length? Well, my magnification factor is 4, right? Because I've now divided that into 4 lengths. N is 9, M is 4, the dimension, log 9 over log 4, 1.585 once again. So thankfully, the dimension does not depend on which of these self-similar pieces we see. Okay, so let's try some. So I want you to pause and do activity 3, and you can find some of these different fractal dimensions. Okay, so here's what we have. The Sierpinski square, this is kind of the sibling to the Sierpinski triangle. So how many self-similar pieces, what's the magnification, what's the d? You can try more than one if you want, but again, if you're not being clever, counting a really small one is going to take you a long time, right? If I use this little tiny square in the corner as my individual one, I got to count all those up at the same length. You can be clever about it and see some patterns, right? So hopefully you're not just directly counting them, but we'll use the biggest self-similar piece, which would be like this corner here. So we have n of those, right? 1, 2, 3, 4, 5, 6, 7, 8. And the magnification is 3, because there's 3 of them to a side. That gives me a dimension of 1.893. If you were brave and did it for another, there's 64 at the 1/9 stage, these little ones I talked about before. And again, log 64 over log 9 is 1.893 again. The box fractal. Well, I can see 5 self-similar pieces right off. What's the magnification for each of those 5? Well, take a line here, they'd be 1/3, so the magnification is 3. So we get n equals 5 and m equals 3. This thing has dimension 1.465. If I went even smaller, then I can get 25 of these things, right? How do I get 25 so quick without counting them? Well, there were 5 in the original, and each one has 5 of the smaller ones. So there's 5 copies of 5, or 25, and they have an m of 1/9. An m of 9. So that gives me, again, 1.465. Notice as well, this is 1.465. The one above is 1.893. Notice how the one that's closer to dimension 2 looks thicker, right? Whereas this one looks a little more sparse. That is true. As the fractal dimension approaches 2, these things start to, they fill in. Now, the last one was the Menzier sponge, and this one's a little tough to kind of count up. This hole goes all the way through, right? So there's 1, 2, 3, 4, 5, 6, 7, 8 cubes around the front. Then there's 1 cube here, a cube here, a cube here, and a cube you can't see, and another 8 on the back. So that's 20 cubes total. What's the magnification? It's 1/3 as long, right? So my n, it isn't 5. I'm sorry. I'm directly lying to you. That's just cruel. This n is 20, not 5. So n is 20 and m is 3, and this gives log of 20 over log of 3, which is 2.727. Okay, that's all bizarre. But what's this have to do with nature? I claimed it was the geometry of nature. Well, fractal geometry is a lot better at working with nature than the traditional geometry of circles and lines. So here's a fern, for example, and you can see the self-similar pieces, right? This is actually a zoom in on ice particles and snow, but again, you can start to see some self-similarity. And this actually, I love this. This is lightning, basically. But so Bert Hickman creates sculptures by basically blasting an acrylic block with 2.5 million volt particle accelerator, and that creates basically lightning captured that you can buy and have in your house. You can certainly see the fractal nature of this. And there are a ton of applications for fractal geometry. Fractal models describe the development of urban areas and the layout of streets and buildings. Antenna design, fractal-shaped antennas, in particular Sierpinski gaskets, which are related to those triangles and squares we looked at earlier. They provide multiband frequency operations in compact designs, which is just really cool, again, to think that, some devices like a phone might have these in there. They don't, but they certainly have in the past. Don't break your phone to look for them. Medical, fractal dimensions help identify irregular tissue growth, assisting in early cancer detection. In fact, if you think about medical as well, think about our lungs. Our lungs certainly seem, and our circulatory system, those are both fractal in nature. And don't even get me started on city growth versus biology with bodies. It turns out that our circulatory system is really similar to the way streets operate through cities. Rendering landscape. Fractals generate realistic landscapes and terrains in movies and video games. For example, fractals were used in Star Wars: The Empire Strikes Back to render the planet Hoth. That was all done using fractals. Geology. This is actually a project I did with a student a few years back who was a geology math double major, and we looked at fractal dimension and how can we use in volcanology to determine fragmentation dynamics, which is the study of how volcanoes break up magma. I keep leaving these parentheses off for you. Sorry about that. Another student of mine worked on handwriting analysis. It turns out fractal dimension can be used to detect forgeries in handwriting. And speaking of forgeries, fractal analysis is also used to detect forgeries in paintings as well. All kinds of applications for this really bizarre, kind of far out there mathematics of fractals. All coming from the study of borders. All right, I think that's enough for today. So thank you so much. Hope you had a great time.